Hey, today we're going to look at a technique for approximating the area under a curve. And we'll look at the function y equals x squared plus 1. And our goal is going to be to approximate the area under that curve and above the x-axis from x equals 0 to x equals 2, so the shaded region here. Think for a minute about how you might make a guess at that area. And in particular, suppose I told you that I think that that area is 1/1,000,000th of a square unit. See if you can come up with an argument that explains why that can't possibly be the case, why it has to be bigger than that. So pause the video for a moment, give it a little thought, and then start it back up when you're ready. Maybe you came up with this argument: the area that we're looking at entirely contains this rectangle that I've built here that has width 2 and height 1, which is to say that we know that the area we're looking for has to be bigger than 2. All right then, suppose I made a second guess and said, okay, it's bigger than 2. I think that the area under this curve and above the x-axis between 0 and 2 is 7 trillion square units. See if you can't come up with a similar argument that describes why it has to be smaller than that. So take a minute, pause the video. When you're ready, start it back up again. And here we see that the area that we're talking about is entirely contained in a rectangle of width 2 and height 5. And so we know that the area has to be less than 10. And so we have narrowed it down to the area is somewhere between 2 and 10. It would be great if we could do better than that. Let's work first on the lower bound. And instead of just showing that the area that we're looking at contains a single rectangle of width 2 and height 1, we can break it into 2 rectangles, each of width 1. And here, the height of each rectangle is based on the function value at the left-hand endpoint, or the left-hand x value of each of the rectangles. And so if we call the area of these rectangles A1 and A2, we have that the area of each rectangle is its width times its height, and the width of both rectangles of each rectangle is 1. And the height of the first rectangle is f of 0, since 0 is the left-hand endpoint of that rectangle, and f of 0 is 1. And so we get the area of that first rectangle, 1 times 1, or 1. For the second rectangle, the width is 1, and the height is f of 1, and f of 1 is 2, and so the area of that rectangle is 2. And now we've improved our lower bound on the area under the curve. We used to have that the area had to be greater than 2. Now we know it has to be greater than 3. And if I break the area under the curve into 4 rectangles, I can do better. Here in this case, I've got the height of each rectangle, once again, decided by the function value at the left-hand endpoint. In other words, this first rectangle, its height is f of 0. This second rectangle, its height is f of 1/2. The third rectangle, the height is f of 1. And the fourth rectangle, the height is f of 1.5. And the sum of the areas of these 4 rectangles gives us an approximation of the area under the curve, and it's called a Riemann sum with n equals 4 because there are 4 rectangles, using left endpoints or left-hand endpoints, because the height of each rectangle is given by the function value evaluated at the left-hand endpoint of the rectangle, or the left-hand x value of the interval that the rectangle spans. For example, the area A1, width times height, because it's a rectangle, and the width of each of these rectangles is 1/2. And so it's 1/2 times the function value at 0, the left-hand endpoint. And f of 0 is 0 squared plus 1, or 1. And so we get 1/2 times 1, and A1 is equal to 1/2, or the area of this first rectangle, 1/2. Similarly, to compute the area of the second rectangle, its width is 1/2, and its height is based on the function value at the left-hand endpoint, meaning the height is f of 1/2, because this is the point 1/2 right here. And f of 1/2 is 1/2 squared plus 1, which is 5/4, and that gives you that the area A2 is equal to 5/8. Okay, you take a minute and see if you can compute A3 and A4, or the areas of the rectangles A3 and A4, and then we'll add them all together and come up with the Riemann sum. So pause the video, and when you're ready, start it back up. And you do the arithmetic that's involved, and you get that A3 is 1 and A4 is 13/8. You convert everything into eighths so that you can add them together, and it turns out that the sum of the areas of these four rectangles is 15/4. And so now we know that the actual area under the curve is something larger than 15/4. Previously we knew, originally we knew it was greater than 2, then we determined it was greater than 3. Now we know that it's even greater than 3 3/4. And we can do the same thing with our overestimates. Instead of just putting the area under the curve inside a rectangle of width 2 and height 5, we can break it into two rectangles, where here the height of each rectangle is based on the function value at the right-hand endpoint of the rectangle. And so this is what we would call a Riemann sum with n equals 2 using right-hand endpoints. And computing the area of these two rectangles, we have each one is width times height. The width of each one is 1. And so the area of A1 is 1 times the function value at 1. And the function value at 1 is 1 squared plus 1, or 2. And so A1 has area 2, and similarly A2 has area 5. Adding these together, we get that the total area under the curve must be less than 7. Previously, we knew that it had to be less than 10. Now we know that it has to be less than 7. Okay, you try this one all on your own. Find the Riemann sum for this curve y equals x squared plus 1 with n equals 4 using right-hand endpoints to determine the heights of the rectangles. So pause the video, take a few minutes, do the calculations, and when you're ready, start it back up. And there's a bunch of arithmetic to do. Each of these rectangles has width 1/2. And the height of the first rectangle, A1, is based on the function value at the right-hand endpoint, 1/2. In other words, the height here is f of 1/2. F of 1/2 is 5/4 because the function is x squared plus 1. And so you do the arithmetic. 1/2 times 5/4 is 5/8. And similarly, you compute the areas of each of the other three rectangles. And when you add them all together, you get 23/4. And so we have a new upper bound for the area. The area has to be less than 23/4, or 5 3/4. And hopefully you can see what's happening here. What's happening is the more rectangles we use, the better the approximation of the area is. So, for example, here we have Riemann sums with n equals 20. The interval from 0 to 2 has been broken into 20 rectangles. And I've got it on the left using left-hand endpoints and on the right using right endpoints. And you can see that they're both pretty good approximations of the area under the curve. The one on the left still slightly too small. The one on the right still slightly too large. But we're getting better and better. And if instead of 20 rectangles, I'd used 20,000 rectangles, we'd have a very, very good approximation of the area under the curve. I want to show you one more nuance before we finish up, and that is it's not necessary to use either the left-hand endpoint or the right-hand endpoint to compute the height of the rectangles. In this case, for example, I've used the midpoints of each interval to compute the height of the rectangle. So for our first rectangle here, the height is based on f of 1/4, which is halfway between 0 and 1/2. And our second rectangle, the height is based on f of 3/4, halfway between 1/2 and 1, etc. And this is not obviously an overestimate or an underestimate, it's simply an approximation. And just like we saw with left-hand endpoints and right-hand endpoints, the approximation gets better and better the more rectangles you use. Here we have 20 rectangles whose height is based on the function value at the midpoints. Okay, this approximation of the area under the curve using rectangles will become a very important concept when we stop approximating and try to compute the precise area under the curve, which is where we're heading next. There's a homework on these Riemann sums, just a few of them to compute, so take a stab at that, and I look forward to seeing you in class.